Lesson 6.4, Polar Coordinates. Up to this point in your mathematical career, you've really only dealt with one type of coordinate system, and that's the Cartesian coordinate system, also known as the rectangular coordinate system. And the Cartesian coordinate system consists of an x-axis and a y-axis, and if I want to describe any location within that coordinate plane, I just had to tell you where that point is along the x-axis and where that point is along the y-axis. And then I would present that information as an xy ordered pair. For example, the coordinate 2, 2. So if I had a coordinate plane, an x and a y axis, I could just count 2 along the x-axis, 2 along the y-axis, and there's my point, exactly at the location 2, 2. And if you wanted to, you could imagine an imaginary grid laying in the background to help you locate these coordinates. So what you can kind of see is why we call it the rectangular coordinate system is no matter where that point is, if I map that point back to the x and the y axes, it creates a little rectangle. So every location can be described using little rectangles. But that's not the only way to describe locations. That's just one option. There's another type of coordinate system called the polar coordinate system. And within the polar coordinate system, instead of using x's and y's to describe locations based on horizontal and vertical distance from the origin, we use r and theta, in other words, a radius and an angle. Because instead of using rectangles, we use circles. So when we have circles, we start, instead of calling it the origin, we call it the pole, the center of our coordinate system. And then the theta is described with respect to the x-axis, which we're now going to call the polar axis. So we measure the angle theta just the same way that we've measured angles in the past in standard position. We measure it to the positive x-axis. We just call it the polar axis. So instead of describing this location, this dot right here, as 2 along the x-axis and 2 along the y-axis, I can describe it based on how far it is from that central pole, simply by saying it's an r distance from the pole at an angle of theta with respect to the polar axis. So if I know the coordinate was 2, 2 in the rectangular coordinate system, I can figure out what it is in the polar coordinate system by realizing that r is just the hypotenuse of a triangle where the x and y sides of the triangle are 2 and 2. So just like we did with vectors and just like we did with right triangle trigonometry, we can figure out all the missing sides from basic rules. So we can figure out the radius to start with by just using the Pythagorean theorem, square root of 2 squared plus 2 squared, which is 4 plus 4, or the square root of 8. And then I can figure out the angle using any one of my trig functions, sine, cosine, or tangent, but keep in mind, since I'm given x and y, the most efficient way to find the direction angle, just like with vectors, was the inverse tangent of y over x. Now again, I always have to make sure I'm in the which quadrant I'm in case I need to make any adjustments. If I'm in the first quadrant, no adjustments are necessary. Second or third quadrant, I would have to make a 180-degree adjustment. Fourth quadrant, a 360-degree adjustment. Now with polar, though, we typically default to radians, so instead of making a 180-degree adjustment, I would have to make an adjustment of pi. 360 becomes 2 pi. So everything from this point forward, unless you're told otherwise, is going to be in radians. So inverse tangent of 2 over 2, which is just inverse tangent of 1, well, this is a unit circle value. Tangent is 1 at pi over 4 when the sine and cosines are the same. So that means I have a coordinate of root 8 pi over 4. Radius is root 8, angle is pi over 4. But root 8, I'm going to pretty it up a little bit, simplify that root 8. That's just 2 root 2 pi over 4. So here's my polar coordinate that describes the rectangular coordinate 2, 2. Let's go ahead and practice plotting using the polar coordinate system. Notice instead of it being a rectangular grid, we have a circular grid, so that each one of these circles represents 1 unit in radius, and then each of these little spokes can represent an angle. Now keep in mind we're using radians more commonly. Now notice point C I switched to degrees just to point out that it technically doesn't matter, but I'm going to stick to radians most of the way through. So if this is my 0 angle, this is my pi over 2 angle. So I have 1, 2, 3, 4, 5 spokes. Alright, so which means the middle one is going to be pi over 4. Alright, and if I took my pi over 2 and divided it, well, instead of it being 5, it's really pi over 2 is my 6th spoke, so if I divide pi over 2 by 6, that means this first spoke would be pi over 12. And if my first spoke is pi over 12, then I can just add pi over 12 to pi over 12 to get my second spoke, or 2 pi over 12, which is pi over 6, my first unit circle angle. And then pi over 4, so that means this one would be pi over 3. And this one would be 5 pi over 12, or in degrees, it's just 15 degrees every spoke. So within the rectangular coordinate system, when I would plot a point, I would plot the x value and then the y value, typically because it's just going from left to right. With the polar coordinate system, it's quite common to do it in reverse. We'll start with the angle pi over 6 and then plot a radius of 1. So I would find my angle pi over 6, which is this spoke right here, and then I'm just going to plot a point with a radius of 1. In other words, I'm going to plot a point on the first circle out from the pole, which is right here. So there would be my point A. Now, why don't you go ahead and try point B, and if you're really feeling a little cheeky, go ahead and try point C. Press play when you're ready. Alright, point B is at an angle of 4 pi over 3. So if it's 4 pi over 3, well, if this is 1 pi over 3, that means this would be 2 pi over 3. That means this would be 3 pi over 3, and then 4 pi over 3 would be this guy right here. So 4 pi over 3, radius of 2, so right here is where you should have plotted it. And the last one, notice I switched to degrees just for kicks. 45 degrees is the same thing as pi over 4, so that's going to be this spoke right here, this angle right here. And I want a radius of -1. Now here's where the first time we notice a negative radius. In your geometry class, this probably would have been complete nonsense to have a radius of -1, but as we've already seen with angles, because they can be negative, there's no reason a radius can't be negative either. So if I have an angle of 45 degrees but I want a radius of -1, that just means instead of walking forward 1, I'm going to walk backwards 1. Well, if this is my forwards, represented by the angle at 45 degrees, backwards would just be this angle right here on the exact mirror image, on the exact opposite side of the circle. So instead of walking forwards at 45 degrees, I'm going to walk backwards, still pointing in the direction of 45 degrees. So I'm still going to walk one circle, I'm just going to walk one circle back. So notice I'm still on that first circle, but instead of walking forwards 45 degrees, I'm walking backwards at that 45 degree angle. Now, special note about polar coordinates, a difference between rectangular and polar. In rectangular, if I give you a location, there's only one numerical value I can give to that location. And if I give you a numerical value or a specific ordered pair, there's only one location that it can describe. With polar, coordinates are not unique. In other words, if I give you a specific numerical value, a specific ordered pair to represent a location, someone else could come up with a completely different ordered pair and describe the same location. And it really has to do with that angle. Consider the point that we've already looked at, 2 root 2 pi over 4. So that was the original point that we plotted. Now, because we're dealing with angles as part of a circle, I can give that angle a completely different value and it still be the same angle because of the concept of coterminal angles. If I started at pi over 4 and I added a full circle, add 2 pi, remember that 2 pi is really 8 pi over 4, so pi over 4 plus 8 pi over 4 would be 9 pi over 4. Still has the same radius, still has a radius of 2 root 2, but I could change the angle to 9 pi over 4, and since it's coterminal to 1 pi over 4, that means they're the exact same location. So both of these coordinates represent the same polar coordinate. And just like I could add 2 pi, I could also subtract 2 pi. So instead of it being 9 pi over 4, I could have had -7 pi over 4, still the same thing. So really, there's an infinite possibility of ordered pair values to represent the same coordinate. And for that matter, not only could I add a full circle, I could also go crazy and only add half a circle. Now, of course, you might be saying, but if I only add half a circle, I'm on the opposite side of the circle. Well, the way we fix that is we simply make the radius negative. If I add half a circle to my angle value, then it's just a matter of walking backwards along that angle, in other words, giving a negative radius. So if I add a full circle, I don't have to change the radius. If I add half a circle, I just make the radius negative. So given a coordinate r theta, I could add 2 pi an n number of times, so n could be any integer value, so I could add it 2 pi 1 time, 2 pi 3 times, 2 pi 50 times. It doesn't change the radius. But if I only add half a circle, or 1 pi, then I would just make the radius negative. So all polar coordinates can be described an infinite number of ways based on how many times you add a circle or half a circle. Alright, so to recap, if I want to convert between polar and rectangular, we're just using those same formulas that we used back in the vector section, and the same formulas that we used back in right triangle trigonometry. The relationship between the radius, the x and the y is the Pythagorean theorem, and the angle, depending on which direction you're going, you can either use the inverse tangent if you're looking for the angle, or you can use sine and cosine paired with the radius to figure out the x and y components. So remember, x equals r cosine theta, y equals r sine theta, just like in vectors, component form was x equals the magnitude times the cosine of the angle, y equals the magnitude times the sine of the angle. R just represents the magnitude if this were a vector. And then rectangular to polar, Pythagorean theorem for the r value and inverse tangent for the theta with adjustments depending on the quadrant. So let's go ahead and practice. Find the rectangular coordinate using the given polar coordinate. I'll walk you through the first one, and then the rest are going to be on you. So 4 pi over 2. So this is a polar coordinate, and I want to convert this to a rectangular xy coordinate. So if I'm looking for x and y, I have r and theta, so I'll just use my standard formulas for that. R is 4, theta is pi over 2. Now this is a unit circle angle. The expectation is you should be able to do this without a calculator. If you're grabbing a calculator right now, put it down because you don't need it. Cosine of pi over 2, well, cosine of pi over 2 is 90 degrees straight up. Cosine is going to be 0. On the sine of pi over 2 straight up is going to be 1. So 1 times 4 is 4. So there's my rectangular coordinate, 0, 4. Now, just to point out, these formulas were a complete and utter waste of time for this particular angle. Pi over 2 just means we're going straight up. Alright, if I know the angle is straight up at pi over 2 and I'm going a radius of 4, 1, 2, 3, 4, don't waste your time trying to convert it using the formulas. Just convert it by thinking about it logically. If I'm going 4 units straight up, well then obviously I'm at the coordinate 0, 4 within the xy coordinate plane. Anytime that angle is on one of the quadrantals, don't waste your time with the formulas, just count it out. Alright, here are 3 more. Give them a try on your own. Hit play when you are ready. So the first one, -3 pi. Once again, this one's on one of the quadrantals. I hope you just counted this one out instead of wasting time with the formulas. But I'm going to go ahead and waste the time with the formulas just for a little bit of practice. So r cosine and r sine. Plug in -3 and pi for r and theta. Cosine of pi is going to be -1. So -1 times -3, +3. On the y side, I've got sine of pi, which is 0. So I have 3, 0. And again, counting it out, pi is going to be going in this direction, but I'm going to go in this direction -3, which means I'm really going to go to the right 3. So there's my coordinate at 3, 0. 16, 5 pi over 6. Now 5 pi over 6 is not one of the quadrantals, so I do not suggest trying to count this one out. Let's just use the formulas. So 16 cosine of 5 pi over 6, it is a pi over 6 angle. Since it's cosine at pi over 6, it's going to be √3 over 2. 5 tells me I'm in the second quadrant, so it's going to be -√3 over 2. Multiply that times 16, and I would get -8√3 for my x value. Let's do the same thing for the y value. This time it's sine of 5 pi over 6. Pi over 6 for sine is 1/2. 5 is in the second quadrant, so it's going to be +1/2. Times 16, and I get 8, or -8√3, 8. Now the last one, notice we've switched to degrees just to get a little practice with doing it in degrees as well, and I also noticed that this is not a unit circle angle, therefore pull out the calculator. So when I type it in the calculator, I'm going to just type it in exactly as I see it, -2 cosine of -40 degrees, or if you're remembering a random identity that we haven't really used very often but can be quite useful. Just for kicks, if I have cosine of a negative angle, if you remember that cosine is an even function, you can save the effort of hitting that negative button, because whether it's cosine of a negative or cosine of a positive angle, it's going to be the same thing. So you don't really have to type that negative if you're thinking about it. But either one of these, if I typed it in, I would get negative 1.532. If you're not getting that answer, my suggestion is, why don't you check your mode? This is a degree, not a radian. Make sure you are in radian mode. I'm sorry, degree mode. So negative 1.532 for the x. We can do the same thing for the y. And if I were paying attention, again, I don't have to hit the negative button if I remember that sine is an odd function. And with an odd function, I can really just take that negative and pull it to the outside so that I don't have to do either of those negatives. But either way I type it in, I should get 1.285. So there is my coordinate in rectangular. So if we can go one way, we should be able to go the other way. So let's turn it around. Here is a polar coordinate. Here is a rectangular coordinate. Let's find a polar coordinate to match it. But not just one, I want to do two. Because remember, polar, there are infinitely many versions of any given polar coordinate, so I want just two. So let's walk through this one together, and then I'll give you three more on your own. So we've got the rectangular coordinate 1, 0. In other words, I have x and I have y. So if I have x and y and I'm looking for r and theta, I'll start with my Pythagorean theorem formula and my inverse tangent formula. So just plug and chug, 1 and 0 for x and y. That's just going to give me 1 for my radius. For the inverse tangent, I'll plug in 0 over 1, which is really just inverse tangent of 0. In other words, where is the tangent equal to 0? Well, it's equal to 0 at 0. So my polar coordinate would be 1, 0. Which, remember, this coordinate is on one of my quadrantals. I didn't have to do all this work if I just realized, well, 1, 0, the xy value 1, 0 is just one unit to the right. In other words, at an angle of 0, a distance of 1. 1, 0 in rectangular is the same thing as 1, 0 in polar. But I'm not done because I wanted two different polar coordinates. So if I remember that 1, 0 is right here, if I want another coordinate, I can either add a full circle or half a circle in either direction. So if I add only half a circle, I'm just going to add pi to the 0, which is just going to be pi. But anytime I add half a circle, I'm going to take the radius and make it negative. So negative 1 pi would be an equivalent solution to 1, 0. Now, just for kicks, I'm going to go ahead and throw in a third one, just to be clear. Instead of adding pi, I could have added 2 pi. If I add 2 pi, then the radius would have just stayed the same. Alright, here are three more for you to try on your own. Remember, if it is a unit circle value, then you do not need your calculator. Put the calculator down. If it is not a unit circle value, then pick up the calculator. So go ahead and try this on your own and hit play when you're ready. Alright, so the first one is at negative 3, 3. We'll go ahead and start with our standard formulas. Plug in negative 3 and 3 for x and y to get the radius, and I get root 18. Or if you simplified that, that would be 3 root 2. We'll do the same thing with the inverse tangent formula, 3 over negative 3, which is going to reduce to negative 1, which means that's a unit circle value. I hope you didn't pick up your calculator. When is tangent equal to negative 1? Well, it's equal to negative 1 at negative pi over 4. We are in the second quadrant, so I want the pi over 4 in the second quadrant, which is going to be 3 pi over 4. So I've got my answer of 3 root 2, 3 pi over 4, but I need a second answer. Remember, here is my coordinate. I can either add a full circle or half a circle in either direction. And I went ahead and just added half a circle, which is going to be adding pi. So if I added pi to 3 pi over 4, I would get 7 pi over 4. Since I only added half a circle, I'll make the radius negative. Next one was at 0, negative 4. This is on one of my quadrantals, so I really don't need to do all the work. If I just remember 0, negative 4, just means go straight down 4. So I have a radius of 4 and an angle of 3 pi over 2. So I know my answer in advance is going to be 4, 3 pi over 2. Let's see if my work agrees with me. So 0, negative 4 plugged in for x and y gives me a radius of 4, exactly what I predicted. Now let's do the same thing with the inverse tangent angle, and here's where I start to realize I got a bit of a problem. when my x value is 0, I get undefined in my inverse tangent problem. If I tried to type this in my calculator, it would just throw it right back at me and not give me an answer. So here's a situation when the formula actually fails me, and I need to have some mathematical understanding of the problem. Calculators are nice, but if you don't know the math, it's not going to help you. By knowing that it's on one of the quadrantals, I know in advance that the angle is, if I'm going straight down, it's got to be 3 pi over 2. Not because the inverse tangent tells me it's 3 pi over 2, but because the coordinate itself tells me it's 3 pi over 2. So here's my first answer. I can go halfway around the circle to 5 pi over 2, and I would get -4. I could also have gone backwards half a circle and had 1 pi over 2, but it really doesn't matter. Pick one and go with it. And the last one, I've got 3, 4. I'll start with my radius, 3, 4. Well, that's just 3, 4, 5. Radius of 5. Then I'll go to my inverse tangent, 4 over 3. So here's a situation, 4 over 3. That is not going to be anywhere on the unit circle, so I can pull out my calculator. And when I pull out my calculator, it doesn't matter if I put it in radians or degrees. I prefer radians most of the time. But when I am using the calculator, I know most of you are probably more comfortable with degrees, so I went ahead and left it in degrees for you, 53.130 degrees. So I have a radius of 5 and an angle of 53 degrees, which is right about here. If I went ahead and added either a full circle or a half circle, in this case I'm going to add half a circle, which means 180 degrees. I get -5, 233. Alright, so if I can convert coordinates, I should also be able to convert entire equations. So let's go ahead and practice converting a polar equation into a rectangular form. I know it's a polar equation because it's got r's and thetas. My goal is to get rid of all the r's and the thetas and turn them all into x's and y's. Now I can't just say r is now y and theta is now x. That's not how it works. I have to use my formulas that I established. The x equals r cosine theta, y equals r sine theta, and r equals square root of x squared plus y squared, and of course the inverse tangent of y over x. Now I'll tell you, the one that we probably use the least amount, the least common useful formula of those four would be the inverse tangent. Not very common to replace theta with inverse tangent because there's so much better ways I can do it. Now on this one I have r equals 4 sine theta. Now if I wanted to, I could just replace r with the square root of x squared plus y squared and replace theta with the inverse tangent formula, and thus have my equation written only in terms of x's and y's. But with math, it's often not good enough just to be right. You want to be elegant. You want to make it look pretty. So what we're going to do is we're going to do something a little bit more creative than that. I notice that I have sine. Now I know that I have a formula that says y equals r times sine. I have sine, but I don't have r times sine. I have 4 times sine. If only there was an r sticking in right here. Because if there was an r sticking right in front of the sine, then I could replace it with y. Well, there's an easy way to fix that. Let's just multiply both sides of the equation times r. By multiplying both sides of the equation times r, which is perfectly legal, I can always multiply both sides of an equation by a number. I get r squared on the left, and I have 4r sine on the right. Well, now r sine, I can now take this entire piece and cross it out and replace it with the y value. And for that matter, I can do the same thing with r squared, because if r equals the square root of x squared plus y squared, then r squared equals just x squared plus y squared. But so by not only by multiplying r on both sides do I get y on the right, but I get an even prettier version of my Pythagorean theorem formula by getting r squared on the left. So r squared gets replaced, r sine gets replaced with x squared plus y squared on the left, and y on the right. So the 4 just comes on down because the 4 had nothing to do with anything. Now technically this is an answer. I have converted it from polar to rectangular. It's an equation with only x's and y's. But again, elegance, we can do better. If I were to move that 4y over to the left side, I might start to notice a handy dandy little formula from way back in Algebra 2, that the standard form of a circle looked like this. Standard form of circle, x squared, or x minus h squared plus y minus k squared equals r squared. This almost looks like that standard form of a circle. Now I've got x squared right here, which really means I have x minus 0 squared, but then the y squared has that 4y attached as well. So if I could get these two together to form a perfect square like y minus k, I could then have this written as a standard form of a circle. So now you got to remember, how can I get these two terms, which right now are not a perfect square, into a perfect square? And maybe you might think about an old technique that you learned called completing the square. So let's take just the y terms and complete the square. Now remember, in order to complete the square, what we were going to do is we're going to take this b value. Remember, this is quadratic ax squared plus bx plus c, or in this case y. So I'm missing my c value. I'm going to make a little space for my c value. And I'm going to take that b value, -4, I'm going to cut it in half, which is -2, and -2 squared is +4. So whatever the b value is, cut it in half and square it. To complete the square, we take the b value, cut it in half, and square it. -4 cut in half is -2, squared is +4, and if I add 4 to the left side, I have to add 4 to the right side. And by doing that, I can now take this quadratic trinomial and factor it as a perfect square because I just completed it into a square. And if I look for factors of 4 that add to -4, well, that's just going to be y minus 2. Again, -2 from the half b. Whatever I cut b in half to b, I'm going to factor it and put it right here. So there's my much prettier form of a circle, but again, as I said, this is an answer. This is a prettier answer. And it's not about being pretty all the time, but sometimes it's nice to be pretty. Alright, let's give this one a try. Why don't you try it on your own, see if you can have a moment of brilliance, and then hit play when you are ready or you've given up. Alright, let's see if you had any bright ideas. I see secant this time. I wish it said cosine, but it doesn't. It says secant. Now, I don't have any formulas for secant. I have a formula for cosine. X equals r cosine theta. So multiplying both sides by r like I did on the last one really isn't going to get me anywhere. I need to get rid of that secant before I do anything else. Again, I want it to say cosine, so let's just replace secant with its reciprocal, 1 over cosine. I also don't want to have any fractions, so you might have gotten the idea to multiply both sides by cosine to get rid of that fraction. So if I multiply both sides by cosine, notice what appears on the left side is r cosine theta. On the last one, I had to multiply both sides by r in order to get what I wanted. This one, it's technically already there. Let's just replace r cosine theta with x. X equals 4, vertical line, I'm done. Alright, here's another one. Why don't you try this one on your own and then hit play when you're ready. Alright, this time I once again have cosine and sine already in the problem, so I may have thought about what I did in example A. If I multiply everything by r cosine and r sine can be replaced with x and y on their own. R squared would be x squared plus y squared. And just like I did in A, I can move everything to the other side and complete the square to pretty it up a little bit. So I'm going to complete the square on the x's and the y's this time. So I'll make a little space on both. To complete the square on x squared minus 6x, I'm going to need half of b, which is -3, squared is +9. If I do it to one side, I got to do it to the other side. For the y's, half of b would be 1, squared would still be 1. Added it to one side, added it to both sides. So 9 and 1 gives me 10, and now I can factor each of these x and y groups separately into x minus 3 and y plus 1. Pretty answer, acceptable answer. Alright, as we always do, we went one way, let's go the other way. Convert to polar form now. Here's a rectangular equation. This is a vertical line at -5. I want to convert it to polar. So these tend to be a little bit easier and a little bit more obvious. X, easy enough. Let's just replace it with r cosine theta. And with polar form, in order to complete the problem, we want to go ahead and solve it for r so that it's r equals a function of theta. To solve it for r, remember what we did with secant and cosine earlier. I can just move the cosine back to the other side as a secant. Alright, why don't you try this one on your own? Hit play when you are ready. 2x plus 3y equals 10. Just like I did on the last one, I can replace x and this time also y with their respective formulas. 2x plus 3y becomes 2r cosine theta plus 3r sine theta equal to 10. And I can do better by go ahead and solving for r. Both these terms have an r in it. Let's factor it out and just divide by the number next to the r. In other words, divide by 2 cosine plus 3 sine. Alright, let's do one more. X plus 2 squared plus y minus 3 squared equal 13. Why don't you give this one a try? If you get stuck, just hit play. Alright, whether you completed it or you're just stuck and need a hint, way I would start this one is not to just replace x and y. If I replace x and y right now, it's going to look much uglier than it needs to be. Before I do my replacement, I'm going to go ahead and clean these perfect squares up. I'm going to go ahead and take the x plus 2 and FOIL it out. I'll take the y minus 3 and FOIL it out. And when I do that, I get x squared plus 4x plus 4, y squared minus 6y plus 9. Now, one thing I'm going to notice right off the bat, 4 plus 9 is 13. 13 on both sides, get rid of them. Don't need them, get rid of them. Now, again, I don't want to do my replacement yet. I want to realize something. I could replace x with r cosine theta, I could replace y with r sine theta, but I'd also have to replace these, and then I'd have to square them, and then I got a lot of craziness going on. If I have x squared and y squared, instead of replacing x and y with my sine and cosine formulas, I can realize that together, x squared plus y squared is r squared. So by regrouping my x squared and y squared, I can get rid of those quadratic terms and just have r squared on their own, and then 4x and 6y, those will get replaced with their appropriate formulas. Now I want to solve for r, so I see an r in all three of them. I'll factor them out. And after I factor, I can set each factor equal to 0, just like you should always be doing when you are factoring. So r equals 0 on its own, and then r plus 4 cosine minus 6 sine equals 0 on its own. Now, if you think about r equals 0 for just a second, r equals 0 doesn't matter what the angle is, the radius is 0. So at any angle, radius is 0. In other words, this is not a curve, this is just a single point. Well, this is the equation of a circle. That's not a circle, that's a point. It's irrelevant. It's extraneous. I don't need it. It's an extra answer. So let's focus back on this one. If I solve for r, I just have to subtract this term, add that term, and I have my answer. So there is my equation of the circle. Alright, just for kicks, let's throw in an application problem. How can these polar coordinates be useful? Well, they're very useful in describing distance. Alright, in rectangular coordinate system, we have a distance formula, the square root of x2 minus x1 squared plus y2 minus y1 squared. So the distance along x-axis squared plus the distance along the y-axis squared. When we are using polar coordinates, we have a different way of finding distance. Consider this like a screen on a radar. On a radar, I'm going to know what the distance is from my pole, and I'm going to know the angle with respect to the polar axis. So let's say this coordinate is at 5:15. This one's at 8:110, which means the angle between would be 95 degrees. And I want to know the distance between these 2 points. Let's call it x. Well, if you stare at this long enough, you might think, hey, isn't this side angle side, a triangle with 3 pieces of information given in the order side angle side? I can solve that triangle by using a law, a specific law, a law that we learned a few months ago, the law of cosines. Side angle side is a law of cosines problem. I can find the distance simply by using the law of cosines. So B and C would be 8 and 5. Angle A would be 95. So why don't you go ahead and try this on your own, see how much you remember. Alright, so we'll go ahead and plug in 8, 5, and 95, as well as x for my missing value. Since I'm solving for x, I just have to take the square root, type it in the calculator. You should get 9.796.